equation for the graph.
Okay, 11.6. So 11.5, we were looking at lines and planes in space. And they're not very exciting to draw. In fact, they're really hard to imagine or to picture drawing. If you remember, we drew one that looked kind of like a triangle, trying to envision what the plane would look like that contained that triangle. The images today are going to be a little bit more interesting, but they're three-dimensional shapes, like truly three-dimensional shapes within the three dimensions. So we're going to first consider something called cylindrical surfaces. Do you remember doing the cylindrical method, like the shell method? Got some flavor of that to it, okay? So consider a standard cylinder in geometry, where your base is a circle of radius 3. In 3 dimensions, this equation would look like x squared plus y squared equals 9. Okay, so in 2 dimensions, it look like x squared plus y squared equals 9, and that'd be a circle. And if you 3-dimensionalize it, it means z can be anything you want. You're going to get the cylinder. So your picture should be like a paper towel roll or like a standard trash can, right? A barrel trash can kind of thing. This is a right circular cylinder. Now we're going to consider the intersection of that surface with the plane z equals k for some constants. Since the equation has no z's in it, the intersection with every such plane is called a trace of the surface. So if you took a 3-dimensional surface and you cut it through the middle, if you will, or whatever level you want, that image that you're getting in the 2 dimensions is a trace. You can also think of it as taking a 3-dimensional object and sort of looking at what like the shadow would create on the ground. Much like that as well. That doesn't get you the whole like slicing it apart in different layers, but the same idea is present. You're 2-dimensionalizing a 3-dimensional object. And on this particular one, it would be the same trace. If I cut through the middle everywhere I cut, I'd get a circle of radius 3. Okay, so I've got a bunch of circles of radius 3 all stacked up on top of each other, 3-dimensionalized sort of. That makes my cylinder that I've created here. So more generally, the cylinder is used to refer to any surface whose traces in every plane parallel to the given plane are the same. And then equations of cylinders will have only 2 variables. So we're going to start with, we have several different images we're going to look at. But the images have some names. Some of them are going to be familiar to you and some of them are not, or at least portions of them. But this is a generalized 3-dimensional equation. You see x's, y's, and z's, right? You see x squareds, y squareds, and z squareds, and you see that constant k happening on the end. So, and then you see some mixes of them, right? Like x times y and x times z and x times, or z times y. That's the third one. This creates these 6 shapes. The first one is an ellipsoid. Okay, so an ellipsoid, have in your mind something that looks kind of like an egg or a football kind of a shape. It's a circle, but it's longer in one direction than the other. Okay, that's an ellipsoid. A hyperboloid of one sheet. We're going to see images of some of these others because they're not easy to describe. The hyperboloid of 2 sheets. An elliptic cone. So if you imagine a cone, right, a standard like ice cream cone or the cone that's a traffic cone, there's circle base, right? There's a circle at the top of it. Now if you take that circle and you make it an oval, that's what this is describing. So the elliptic cone is a cone that has an ellipse or an oval kind of a shape on the top of it, or on the bottom of it, however you think about that. Elliptic paraboloid is going to be like a parabola turned into 3 dimensions where we're going to have traces that are ellipses. And then there's a hyperbolic paraboloid. Okay, so I've tried to describe some of them, but we're going to draw some of them as well.
Where do these names come from?
I don't know. Somebody created the names, and then they standardized them, so they're the ones we go with. I don't know the answer to that. There are some interesting things that happen between different branches of math and science, though, sometimes where it's created in 2 different places and named something different, like that happens. And then there has to be a consensus to come to later as to what we're going to call it moving forward. This is an ellipsoid, okay? So an ellipsoid looks like an egg or kind of a blunted football, right? It's not quite as pointy on the ends as a football would be. But it looks like an oval 3-dimensionalized, right? So if A, B, and C are the same but not 0, it actually creates the sphere as well. And the general form that you see for this one is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Okay, so when we get to the end of all of this, what we're going to need to be able to do is to notice what the equation looks like and match it. That's going to be our goal, right? We're going to see all these details about an equation, and we're going to be like, okay, that's the equation that matches the form for an ellipsoid, and that's where I'm going to go to. This is actually centered at the origin, okay? And you can see it from the picture, right? Here's my origin right here. I've got the three-dimensional picture. But the reason from the equation that you know it's centered at the origin is it's x squared, y squared, and z squared on top. If it were centered somewhere else, it would do things like we do with circles, where we do like x minus 7 squared, and we'd have a y minus 2 squared, or maybe a z plus 7 squared. So we'd have features like that happening on top. Without those features, it's centered at the origin. Okay, good so far? Okay, next one. So this is a hyperboloid of one sheet. Actually, let me leave my image in here that I drew last time. Okay, so looking at the equation, what is different about this equation than the last one? There's a negative in front of the z squared component instead of a positive, right? Okay, we want to be able to distinguish that. It creates a very different image, right? So when my kids miss negatives and I tell them they're really important and they look at me and they roll their eyes, this is exactly what I'm talking about, right? Like negatives matter. They change things. In this case, they're changing it substantially. This picture doesn't look anything like the last picture, and all it is a negative that changed. So what's going on here? Well, it looks like a cylinder. Can you see the cylinder involved in this? I didn't mention it over here, but can you see it involved here as well? So a cylinder, what they described as previously, is that if you took a trace, like if I drop a perpendicular down through here, and they drew the one in the middle, that all of the shapes are the same. Wow, that was not what I meant to do. That'll work. Right? They're all cutting through and creating, in this case, ellipses. They almost look like circles the way that this is drawn. And the same thing would be happening here. If I drop the circles, or if I drop this down, I'll put those back in a minute. So if I cut through here, do you see all of the, in their case, they're either ellipses or circles, depending on the image that we're working with. Do you see that they're all the same? I can't get it, draw another one, but can we picture it okay? Okay, so what's the deal with the hyperboloid business? Well, hyperboloid has to do with the fact that you're getting a hyperbola. Do you remember hyperbolas? So hyperbolas, this is like an Algebra 2 thing, college algebra some of the time. You might have seen it in a trig course. Our class here at trig is where we teach it in OBU. Hyperbolas kind of look like parabolas, right? Top and bottom, right? They look kind of like parabolas, but they're actually trapped between asymptotes, which parabolas are not. So I'll draw one in here. There's an asymptote there, not drawn well, but can you imagine this trapping this shape in between? It creates a hyperbola. We will talk more about hyperbolas, but it's in chapter 10, and we're doing all this out of order. So it might be that I need to think about that again when we teach it again the next time. But nonetheless, here we are today. Okay, so we've got hyperbolas happening if you're looking at this sort of a vertical perspective, the way this is drawn, and you have ellipses happening if you're going around, right? And you're cutting through each one of them. Something else to notice on this one is that this is oriented vertically, right? The orientation is based on the value that's negative. So the negative here is on z, so the orientation is vertical around the z-axis. If this had a negative on the x, which would be totally fine, it would simply be oriented to extend along the x-axis, which we are saying is out this direction, and the y is out this way. So the direction that we draw it is based on the negative and its location. Cool? Okay. Oh, mention one more thing. One sheet. It says a hyperboloid of one sheet. This is one connected object. The primary difference between that and this one is that they are disconnected objects. All the other features that I mentioned are actually the same. If I cut through this vertically, the way this is drawn, I get ellipses everywhere. And if I cut through it, or not cut through it, but if I look at it sort of vertically instead of horizontally, you can see those hyperbolas showing up, right? They're showing up on the edges out here. And you can see where the asymptotes, are showing up here too, right? You see those asymptotes showing up, kinda-ish? That's the hyperbola that we're talking about here. Now look at the equation. What's different about this equation compared to the last two? Yeah, on this one I've got two negatives, right? Ellipsoids had no negatives. Hyperboloid of one sheet had one of the pieces negative. Now I have two of them negative. All right? And the two that are negative actually tell us how it's being disconnected. So you see your picture, it's oriented up. That's up and down. That's still because the z is negative, right? And then the y value being negative gets us the break right there in the middle. Okay. I think I've actually written that on this, right? The axis corresponds to the variable with a negative coefficient. The axis here corresponds to the variable with a positive coefficient. I said that backwards. I just drew it wrong. That's okay. The way that this is drawn in is probably because this is the image I could find. This is actually the x-axis that it's oriented around. This axis right now is x. I was actually thinking about that when I was doing it. Okay, and then we've got y and z coming out here. So here's y, and here's z. So it's oriented around the axis with a positive coefficient. Okay, the next one is the one that I mentioned, looking kind of like an ice cream cone. You get both the positive and the bottom. I mean, it's the positive and the negative, the top and the bottom. So you have two cones, a cone opening upward and a cone opening downward. And we have on this ellipses. It's an elliptic cone. So all the traces, right, if I were to cut through horizontally from my picture here, I'd get ellipses again, just like I have on the previous ones that I've drawn. So I'll draw it again on this one to see it. I think probably drawing that in white would be easier. Let's try that again. That's a little bit better. So this is cutting through, going to give me ellipses. They're parallel ellipses that are all stacking up of different radii, right, or extensions. They're not exactly radii because it's different in both directions. But we have different lengths and widths of our ellipses, but they're just ellipses stacked on top and bottom of each other. All right, looking at the equation, what do you notice? It's equal to 0. Good. So the difference on this one, what was it equal to on the last ones? Ones. So the XYZs, those components, match some of the other things we've seen. In fact, it looks a lot like on the left-hand side the elliptic paraboloid, right? Or sorry, the hyperboloid of one sheet, this one. Right? It looks like this one in terms of its equation, but the difference is that it's equal to 0. Okay? Oh, and it tells you here too that the axis corresponds to the variable with a negative coefficient. So the z is the axis that it's extending around because z is negative, much like the last one that I mentioned, the hyperboloid of one sheet. Okay, elliptic paraboloid. Okay, so once again, I'm getting lots of ellipses, and this one's not going to draw very well, so I'm going to have to do it freehand. There's an ellipse happening right here because they've done it at an angle. You see the ellipses all stacked up still? But it looks like a bowl. Yeah? So it's kind of got this fluid shape where it's very rigid here, right? It's cone. It's got these straight edges. This one's not straight on the edges. It's curved. All right, look at the equation. There's a couple of things that look different about the way this is set up. What's something you notice? It equals z. So I've got variables on both sides.
C's gone.
There's not a c. There's no constant. We had constants on the first three of 1, and then we had a 0 on the second one. There's one more thing that's very distinct here. And it has to do with what Sophia said. So what is it?
It's not squared.
Ben noticed it's not squared.
So there's not.
Yeah, do you see the z? Z is not squared here. On all the ones previous, all my x, y's, and z's have been squared. This z is not squared. So you could say, well, it's not that much different than this one right here. I've just moved the number to the other side. True, but I've moved it to the other side, like the z part of it, but it's also not squared. Okay? So we have the axis again corresponding, and this time it's to the linear variable. So it's opening along z because z is not squared. Good? Okay. Oh, I should have mentioned, these are parabolas if you actually look at it in the other direction. That's why it says elliptic paraboloid. Do you see all the parabolas that are drawn in here? Let me move my deals. You can kind of see them up here. Do you see those parabolas? Those are parabolas showing up there, hence the name. All right, this one, hyperbolic paraboloid. Okay, so this one actually looks like an object that you've probably seen before. Can you tell what object it looks like? It looks like a Pringle. That's a very good example. Food's always good. Looks like another object too.
Saddle.
Looks like a saddle, like on a horse. Yeah. So people will often call it a saddle, but I like your Pringle analogy. That's probably what I'm going to go with from now on. All right, so equation-wise, what do you notice?
Minus.
Yeah, it actually looks a lot like this one, right? but the difference is that it's subtracted in the middle, yeah? And it's very interesting because it's got the word hyperbola in it, and it's got the word parabola in it. So in one direction, right here, let me use that block again, you see these parabolas going on, right? But if you look in the other direction, they're actually hyperbolas going on. I can't draw it very well, so I will not draw the hyperbolas, but they're there. Okay? All right. I think there's one more, maybe. No, that's it. That's our last one. Okay. So here's what we're going to do. We have, how many do I have? 7. We have 7 equations, and we are going to describe and sketch the shape. And this first one is actually, generally speaking, it's something we can do, but it doesn't fit into any of the equations very nicely because it's simpler than that. So if you take a look at this one, it says we have y equals x squared. So what I would like for you to notice is it doesn't have a z in it. Okay, so it kind of fits back into the very first description about cylinders that I mentioned, that there's no z in it. So ignore the fact that this is 3-dimensional for a moment and pretend it's just 2-dimensional. If you were just drawing with this in 2 dimensions, y equals x squared, what is the shape? It's a parabola. What's going to happen if you 3-dimensionalize a parabola? Yeah. So you're going to have a shape that looks like a parabola. Okay, right here's my parabola. And you're going to imagine it flat, because I can draw it easier this way. And if you imagined it flat and it's sort of being like paper or something like slinky, and you could drag it out, can you imagine having that 3-dimensional shape coming out of it like that? Still a parabola at every trace, right? But it's cylinderized. That's not a real word, by the way, but we're going to use it like that anyway. Okay, we've turned it into a cylinder. Okay, so how do we draw it? Well, the part that we're 3-dimensionalizing it around is the variable that's missing, which would be z. So as I'm drawing this, I am going to draw the z as the 3-dimensional, like the height part. There might be occasions where I don't orient it that way because it works easier to draw it. We'll see if that happens. But here's my z. Here's my y. I'm sorry, x is what I meant to do. Sorry, x. And then here's my y. So I'd like for us to focus on the xy part first. So if this were xy in 2 dimensions, you would have no trouble drawing me a parabola, correct? It looks something like that. And this is my x-axis and this is my y-axis. Okay? So this graph needs to be over here, opening along the y-axis, just like it opens along the y-axis here. So the image is going to look something like this. Agreed? So sometimes drawing the 2-dimensional part of it is helpful in getting the orientation right, because I about did it wrong. In fact, I think it's wrong on my paper as well, but this is correct, right? We're extending along the y-axis. And then we're going to take that same image and actually, I want to draw it all at one time so that I can get that same image. We're going to get that same image, and we're going to draw that same image at a height higher. Something like that. It's running into itself. That's not good. Let's try it again. That's not too bad. Yes, it looks like it's cutting through the z-axis. It's not really. I'm just shifting it up, and it gives that illusion. But the way that we get the 3-dimensional effect, our best bet at getting the 3-dimensional effect is drawing the exact same image higher and then connecting the endpoints that we had.
3-dimensional drawing is terrible.
Okay. Can you visualize this? So what it kind of looks like is it kind of looks like a piece of paper rolled, right? Drop my paper, but if I took my paper and I roll it like this, it's a parabola-ish, and then I've got it opening upward. Okay. What is this shape called? Because it says to describe it. Describe means I need to give it a name.
Is that the saddle looking one?
Nope. It kind of looks like one, but it's not. It's more basic than that. Nope. It's not an ellipsoid. Does a cylinder have 2 L's? It does not. It's just a cylinder. Now, it's not a very traditional cylinder, right? Most of our cylinders we think of as being like circle traces. This is a cylinder with an ellipse, or not ellipse, excuse me, a parabola.
Rotated, elliptic.
A parabola. No, it's just a cylinder.
Oh.
A cylinder is just a three-dimensionalized image that would have been in 2 dimensions. So if you want to call this a cylinder, it's a paraboloid cylinder, right? Because it's a cylinder with traces that are parabolas. Most of our cylinders have traces that are circles, the ones we're at least most familiar with. Okay, this is a cylinder. Okay, the rest of them are going to be more matching up to things we saw equation-wise. Okay, this is the one weird one. I wanted to mention it first. And notice you can identify that this is happening because it's only got 2 variables, right? Everything else we did has all 3 of the variables present in some way, correct? Yeah. All right, so we're going to take a look. The next one, this is 9x squared plus y squared plus 9z squared equals 9. Now, it is not in standard form of any of the others that we looked at, but it does have the form or have the ability to look like the form that we saw.
Divide all by 9.
Which one is it?
Divide it all by 9.
Okay, we can divide it all by 9. I think that's not a bad place to start. So if we divide it all by 9, because in every one that we looked at, we didn't have a coefficient in front of any of the variables, right? That's true. So this would actually end up being x squared. I'm going to write it over 1 because that will actually match a form a little bit nicer. The second one's over 9. This one's also over 1, and this is equal to 1. Okay. Which one does this match? It's an ellipsoid. Okay. So I'm going to be able to say that this is an ellipsoid. Ellipsoids have all 3 of them positive, all 3 of them squared, and it's equal to 1. And that's actually the best reason for dividing by 9, which Adrian did first, is that the constant on the right is 9. And in all of the other ones that we had, if there was a constant at all, it was 1. Some of them had constants of 0. But if there was a constant at all, it was 1. Dividing by the 9 gets something equal to 1, and the rest will compare. Okay. So how do we draw this guy? Well, the denominator actually tells you how far out, kind of like a radius, it goes in each direction. Okay, sorry, I'm trying to get this pen to change. There we go. So this one is acting like 1 squared. This one's a 3 squared, and this one's 1 squared, right? The denominators are all squared pieces. If you look back at the formula, they all said squared. So here's how we would draw this. We're going to draw it with the standard z-axis on top because there's no reason not to. And we're going to put z up here on top. We have x over here and y over here. And we're going to go out from the origin along each axis the number of locations that it said underneath it that was squared. That was a funny sentence, but just look at what's underneath it, right? Underneath x is the number what? 1 or 1 squared. So we're going to go out 1 along the x-axis. What number is underneath the y squared?
9 3 squared.
9, which is 3 squared. So I'm going to go out 3 on the y-axis. And I'm actually going to do it on the positive and negative. So let me do that as well while we're here. I'm not going to like my 3 dimensions in this very much, but that's okay. Here's 1, and here's 1, 2, 3. And then we're going to go up how far on the z-axis? 1. And down also 1. Oops. And I want to connect these values like I would to create an oval in 3 dimensions. All these things that I just plotted the directions for, all 6 of them are going to have yellow dots. And I'm going to connect them. And I want to connect them smoothly, right? That's not very good. That's pretty good. That's terrible. Okay, it doesn't quite hit the dot, but you can pretend like it does. Otherwise, I'm okay with that one. And the way that we get the 3-dimensionalized effect to it is that we're going to draw in one of the ellipse cross sections, one of the ellipse traces. And I will draw it in dotted so it doesn't confuse things. But I will do it in this yellow color since I'm using yellow at the moment. So, oops, I got to have a curve, not a line.
Looks
Huh?
like a pill.
It does kind of look like a pill. I think it looks like a yellow sweet potato.
Yeah.
Actually, a little bit. I don't know. Okay. We're okay? Adam doesn't agree with me. His face said it all. Yeah, that's okay. All right, ready for another one? First step. We're going to have to identify. This actually set equal to 1, so this is a step ahead of the last one. We're going to have to identify what in the world is this shape.
The one sheet.
It is. Do you remember what the word is before it? Nope. Hyperboloid. Hyperboloid of one sheet. Okay. I'm not going to, I don't, it doesn't ask me to write it down. I am going to write it down. But which axis is it extending around? Yeah. So this one right here tells me that it's going to go around Z. So I said Z and I wrote X. Let's try that again. So here's my standard axis. So we have Z, X, and Y. And this is when we're going to sort of lose a lot of, well, we have to lose a little bit of it anyway, a lot of the dimensionalness of it because it becomes more difficult to draw. We are going to lose it really quick. We're not going to lose it right away. I mean, we're not losing our minds or anything. That's not what we're losing. But check it out. Okay, so ignore the Z part. Look underneath X and Y. And we're going to do what we did on that cylinder. We're going to identify what's being squared. So there's a 1 underneath here. That's fantastic. Right? So this 1 is the same as 1 squared. What's underneath the Y?
2 squared.
That's 2 squared. Okay, so I'm actually going to go out 1 along the x-axis and 2 along the y-axis. And I'm going to do it again in all 4 directions, right? Forward, backward, left, and right kind of stuff. Spacing. Okay, so I've got 1, and then I've got 1, 2. And can you imagine drawing in an ellipse here? Can you imagine doing that? Okay, we're going to do that. I'm going to draw it in dotted because it's not a part of our exact graph, but it's going to give us some perspective here. That's not too bad. So we're going to take this image and we're going to bring it up and we're going to bring it down. But it doesn't go straight up and down. It gets bigger as it goes up and it gets bigger as it goes down, right? It extends like this. So we're going to draw, this is our base for drawing it. Everything else after this is approximation kind of thing. But we're drawing kind of like this. And this image that I drew in the middle, this dotted image, if you can imagine taking that and then stretching it out and putting it a little higher, that gives us some of the three-dimensional perspective that we're after. Up and down. That wasn't very good. Now, I didn't draw mine to have so much curvature. You can certainly draw yours to have more curvature to make it a little more convincing. But the image should still look a lot like the hyperboloid of one sheet that we drew before. Does it? Okay, you didn't know you were in a drawing class today, did you?
It looks terrible.
It looks terrible. I'm so sorry.
Sorry
Okay,
if you guys are-
let's try another one.
We have these on the test.
There will be something of this on the test. I know.
It's all right. It's going to be bad. I'm going to do my best.
All right, how about this one? Y equals x squared plus z squared. Match that up to an equation. What is it?
Is it on what? The ellipticoid parable?
Yeah, it's an ellipse and a parabola, right? It's an ellipse and a parabola. And so the image is actually called an elliptic paraboloid. That's the shape that we're dealing with. Extending along which axis? Like which is the, remember this is the one that looks kind of like a bowl.
It's going on the y-axis, right?
It's along the y-axis. So this y right here tells us that it's going to be along the y-axis. Sorry, my tools just keep getting messed up, so ignore my dots and lines, and they're just all good right now, okay? Okay, so I am still going to draw it with the z up and down. You're welcome to change the direction and make y up and down if you want it to open upwards. Feel free, it doesn't matter. But this one isn't too bad still to visualize opening along the axis the way I normally draw them, so I'm going to. So here's z, here's x, and here's y, and it's supposed to be extending along y. So when I draw this, it's going to look like that parabola that I drew on the very first one at the top, right? Along the y-axis, it's going to extend that direction, like so. But I need to three-dimensionalize this so that it looks like a bowl instead of like a cylinder, right? To do it as a cylinder, I just copied this image, moved it up, and I attached things. But to three-dimensionalize this to make it look like a bowl, what I do is I actually do a circle on the end of it. That's not very good. That's pretty good. Okay, so can you imagine it opening that direction now? That bowl shape that's on the end of it? Okay? I told you you're going to use your imaginations today, right? That was part of my prayer, wasn't it? Using our imaginations. Okay. 3 more. That doesn't quite look like anything we saw.
No.
What can we do to manipulate it so that it will?
You equate the square inside.
We can square both sides. Now, it's important to realize what we've actually done when we square both sides that really didn't mean to do. Okay.
Elliptical cone, isn't it?
Yes, it is. It's an elliptic cone. You're correct. But what happened when we squared both sides? Do you know what's different about this equation than the original equation? Because something did change that is not what we sort of intended. There was a plus or minus that wasn't there, right? So normally, if it starts out looking like this piece right now, and we were to take a square root, we would have to put a plus or minus on there, correct? But that's not how it started. It started without a plus or minus, which means it's just the positive part. I actually answered a question from my kids' school about this notation, not in relation to this equation, I get that, but in this notation as it related to their Algebra 2 class, because they were thinking that the plus or the minus was there. And I was like, if it doesn't show it, that's not the notation, then it's not there. It means it's only the positive part. And we call it a principal square root. So the original equation did not have a plus or minus. So it was the principal square root, which means it's just the positive part. So what we actually know right here is that this z, it isn't negative. This z has to be greater than 0, right? Because it was equal to the square root part, and the square root part was going to be positive, so the z is also positive. So when I draw this thing, I won't get the whole elliptic cone. What will I get? Half of it, just the top half, right? I'll get what I sort of typically think of as our cone, right? Go to Brahms, get a cone. This is the cone, except it's going to have an ellipse shape to it instead of it. The waffle machine just made it squished, and then we're all good, right? No circles. It was a squished one. Okay, so we're going to draw this now. It is opening along the z-axis, right? Right?
Yep.
That's okay, good deal. It does have the feature that there's a 4 in front of the y squared, right? Oh, let me label my axes. This is, come on. This is z, and this one's x, and this one's y. So the fact that there is a 4 there, do you know what that's going to actually do sort of visually? We're not going to do a lot of details, but what's it going to do? It's going to stretch it along the y-axis. So very much like these other ones that have had a 2 underneath and so forth over here, like this one is a 2 squared underneath, it's going to stretch things. So it's not going to be drawn in perfectly, but what we want to have envisioned in our mind is that we've got a cone here, and we have it like this. You can't even really draw it in such a way that you can really see that it's an ellipse versus a circle. It doesn't really have the ability to be done very well like that. Feel free as you're looking at these to find a program that does 3-dimensional graphing to kind of get you a better visualization as you're working. Not doing it here in class because in class you're not going to be able to have that as a tool all the time. So we're trying to sort of visualize it on our own, but you're welcome to use that outside of class. Okay. If you wanted to put this in a more standard form, you could certainly do that. I've got that written down, so let me do that real quick. This would be x squared. Wow, that was not what I meant to do. X squared plus 4y squared plus z squared. Not plus, minus z squared, it equals 0. And then the form for these actually had only coefficients of 1, so I can divide everything by 4. This would be x squared over 2 plus y squared over, why did I say 2? How about 4? X squared over 4 plus y squared over 1 minus z squared over 4. There we go. And so you can see that it's extending differently along each of the axes, but there's no good way to draw that. But this would be our standard form of it. Ready for another one?
No, I'm kidding.
That one is, oh, I didn't write it down. Thank you. It's an elliptic cone, yes. Elliptic cone, that's better. Thank you. Forgot to write it. Said it, never wrote it. All right, how about this one?
Hyperbolic parabolic?
We're running out of options, aren't we? Yeah, we are. You're right. It is a hyperbolic paraboloid, which is what image? It's the Pringle, okay? So we're going to put this in parentheses to visualize later. Right? We're looking at a Pringle, or more traditionally, people would say a saddle. But that's the image we're thinking of, okay? Let's get it into standard form. Standard form also does not have a 4 in front of the y squared, so we're going to do exactly like we did in the last problem, where we divide everything by 4. So I have x squared over 4 minus y squared over 1 plus z over, I take it back. That's not what I went to do. I apologize. That's not the form they showed in. We moved the z to the other side. That's what they did. So z is negative 4y squared, not negative, positive 4y squared minus x squared. Did I get that right? Okay, I think that matches what I had before. Does that match the form that they gave us? Now I'm doubting myself. Does it? It's all good? More or less. Okay, we'll go with it. All right, so how is this opening? What did it say over here? Let's go back to it. The one that, oh, that was it. How is it opening? What does the axis correspond to? The linear variable z, right? Z by itself. So the z value is how it's opening. And so it's going to look just like this picture, right? It's opening along z. And so we're going to draw that image, whoops, right there we go, over here. So we have our graph, z, x, and y, and now we get to see some good skills in drawing. At least I hope some of you have some. Okay, so this is sort of the basic shape. The way that I get mine to look three-dimensionalized is I make curves that look a lot like what I'm already working with. So here's my original curves, right? And I make more curves that look like this on the front side. And then on the back side, if I do it dotted and mimic the backside curves, that might have made it worse. I don't have any backside curves in my picture. Yep, I don't like it at all. Let's go with that. You can picture the saddle or the Pringle. Okay. Okay, we got one left to draw. Process of elimination tells you what it is. Try not to use process of elimination. What shape do I have here? This is the hyperboloid of two sheets. And we can turn it into standard form to see that a little bit better. So we have, let's see. Let's just move our z to the front. So this is 9z squared minus x squared minus y squared equals 9. And then I can divide everything by 9. So I have x squared over 9 minus, z. I said it right. I wrote it right, said it wrong. Z squared over 9 plus x squared over, that's a 1. That's what I wrote wrong. Z squared over 1, x squared over 9. And then y squared over 9 equals 1. That was way harder than it should have been. Okay. Are all the pieces okay now? Okay. Which axis is it opening up along? Z. Why? It's the odd one out. It's the positive one, right? In that particular description, it says it opens along the positive axis. So it is still opening along Z on this one. So I am going to have these shapes that sort of look like flying saucers a little bit. Can we go with that? A little bit, right? That's not really drawn well. Let's try it again. Let me do it that way. Whoa. I don't know. This is not getting any better. Oh, that's not bad. I'll go with that. And let's do this. That looks pretty close to what my picture has. They kind of look like these bowl shapes on the top and the bowl shaped on the bottom, right? That's kind of what they look like, give or take. I should label my axes. I didn't do that. Let's do that real quick. So here's X, and here's Y. All right, so what is your homework going to look like? Well, I think some of it's matching. I think that's what 5 through 10 is. I'm pretty sure if I remember right, okay? So matching's good. And then the other ones right there, I think there are some where you're going to identify, there's some where you're going to draw, maybe there's some that you do both. I don't remember exactly, but I do remember being a combination of some different things along the way. Obviously, as you're looking at WebAssign, it's not going to have you draw a squat diddly, right? Not a bit. So that's not real helpful if I'm going to expect that you know what these images look like better than a multiple choice, because, I mean, you're not getting a multiple choice graphs from me on a test. So we're going to have some practice of both. Sound good? All right.